Any questions about anything? Yes?
What is today's lecture on?
What is today's lecture on? Well, we're going to continue talking about these linear time invariant systems and a few things you can do with those. And then we're going to segue into chapter 6, which is about frequency response. Yes?
Are we going to have a review on
Thursday
Thursday?
at the part of the class after the break, I'm just going to throw it open to questions. How about that? That's what I'm going to do. So I'm not going to do like a formal review. I don't know. I haven't heard anything about the TAs mobilizing for something like that either. So, but bring your questions on Thursday. I'll send an email to the class that that's going to happen, so the people who don't come usually can come if they want. You know, ask questions, whatever. Anything else? Yes, Nick.
Can we also get our homeworks back before the prelim?
I hope. You know, it's funny. Like this one, this is still homework 1. I'm bringing it like a talisman, hoping that other folders will magically appear. You know, but they're not. So far, this came back really quick, and for some reason, 2, 3, 4. Even though the TAs know which problems are to be graded, or at least 2 and 3, haven't appeared yet. So I'm not sure. Let's keep our fingers crossed.
I'm not sure if it's been asked yet, but will the practice prelim solutions be posted?
Okay, first of all, picky about this. It's not a practice prelim. It's last semester's prelim 1. The reason I don't like to call it, I don't do practice prelims. Why? Because then if there's something on the actual prelim that wasn't something just like it, isomorphic to it on the practice prelim, people say, this wasn't on the practice prelim. You know, there's something about calling it a practice prelim that makes people think, if I do well on this, then I'll do. So it's last fall's prelim 1. That's thing number 1. Thing number 2 is, someone asked that question last night on Piazza, and I told them I haven't decided yet whether I'm going to put up solutions, but it would be fun. It would be fun if people put up some conjectures about the answers to the problems, or debated them, or talked about them a little bit on Piazza, instead of just sitting there waiting to be served them up, right? Okay? So how about, like, if you start some animated back and forth about, oh, what is the answer to 1E? I don't get this. Or something. I think that is an actual problem that is interesting. So, yeah. If you get that going, then maybe I'll, like, give you solutions. Who knows? Anything else? Okay. That's not good. If the teacher sneezes, that means everyone has to put their mask on. No, it's actually, I went to Massachusetts over the weekend, and when I was driving back on Sunday, like when I got home, I was sneezing, and I diagnosed that to be just the fact that the air was so dry in the car and everything, and all that. And it wasn't that because I'd been in Massachusetts, I was in a high-risk area, and then I read that in the college hockey playoffs, RPI, which hasn't hosted a playoff series in years, finally got to host a series this year against Harvard, but then their college said, no, you can't have fans at these games. You know, they have like the biggest rink in the whole ECAC. So in my opinion, that's a bit of an overreaction. So Harvard and RPI are going to play their hockey series in front of nobody, except the refs, maybe the PA announcer, I don't know. And so I was starting to worry about, like, what if they do this here? What if they overreact? They say, oh, well, there's been a coronavirus case in New York City. Therefore, Cornell is going to, like, shut down. They're not going to have any sporting events with audiences.
There might be some in Tompkins County.
What's that?
There's 46 people quarantined in Tompkins
Yes,
County.
yes, I know. And the thing is, this is not like Ebola. This is a really mild thing for most people. So I don't know. Anyway. Enough of that. So I was worried when I was sneezing when I got out of the car, but then I diagnosed it as dry air in the car, and so whatever. Anyway, all right. So what did we talk about last time? We talked about we were talking about these causal FIR systems, and then we segued into a more general kind of system, which are LTI systems. Okay, so we introduced linear time invariant systems. And these are a more general class of systems than the FIR systems. So in particular, the causal FIR systems are examples of these. And we actually showed that. The definition of an LTI system, it's linear in the sense that if you sum two input signals or take a linear combo of two input signals, then the resulting output is going to be the same linear combo of the individual outputs. And it's time invariant in the sense that if you shift an input signal, then what happens to the output is it gets shifted by the same amount. So that's the L part, and that's the TI part of LTI systems. Now, we also talked about convolution. And remember what the definition was, given two signals. And I want to emphasize that this is an operation that takes whole signals and gives you another. Yes, Jack?
I got an email 1 minute ago. They just canceled fans.
Wait, here?
Yeah.
That pisses me off. Big time. I don't believe they're doing that. Are you?
To inform you. Fans will not be permitted at this weekend's ECAC Men's Hockey Championship quarterfinals.
That's absurd. It's absurd. Okay, I'm thinking this. He's pulling my leg. No. Okay. Outlook.
Big red ticket.
Uh-oh. All right. Everyone put on your helmet because I'm going to throw the phone. I don't know where it's Unbelievable.
Follow-up question, what happens when this class goes online only? It's already online.
Yeah, it's already
Will it
online.
last for all?
This is yeah, I know. Well, Stanford has quarter system, so they only have 2 weeks left in their current quarter. So they basically burned that 2 weeks. They said, OK, all classes that can go online, all the rest of you figure out something. You know, like we have too much left. And honestly, this is it's a total overreaction, in my opinion, to this situation. It's crazy. I mean, you look at, like in 2009, we had this H1N1 thing. Everyone was all wringing their hands about it. I don't know if you guys remember that because you were pretty young.
Is that the swine flu one?
No, swine flu is another thing. That's been around too. And bird flu and avian this, that. You know, H1N1 was this big deal. And we had these emergency meetings in Day Hall, like the dean and the faculty were saying, what if we have to cancel classes? And I'm like, this is not going to happen. And it didn't. You know, it just sort of petered out, and that was it. Worldwide, H1N1 killed about 575,000 people. Jose Martinez told me that yesterday. That's like zillions more than this particular COVID-19 or whatever you call it is going to do. Anyway, I'm sorry. This is all on tape now? I know.
Honestly, so that people enjoy it more, I'm probably just going to like edit it so that it's just the signal stuff, just so that people don't have to wade through a bunch of irrelevant stuff to class.
Would you like Alex to no, you want to show this to your brothers and sisters at home, right? You say, this is what happens in classes at Cornell. The professors really care about these global issues. And furthermore, no.
Actually, I'll send you the unedited stuff and you can make that decision. It's easy to just go.
No, I'm too big. Just do your thing, whatever you want to do. And anyway. All right, given two signals, h of n and x of n, their convolution, y of n, if it exists, is defined by this formula, sum from k equals minus infinity to infinity, h of k, x of n minus k. And remember, this is an operation that takes two whole signals and gives you another whole signals. And notation-wise, we usually write this, y of n equals h of n, convolve with x of n. Okay, so two whole signals. I just realized that this fan thing at the hockey games, this might be a plot. I mean, this is a conspiracy theory on the part of ESPN, because ESPN has the streaming service called ESPN Plus. All ECAC home hockey games are streamed via ESPN Plus. It's behind a paywall. So now, hockey fans who want to watch their team play will have to sit in front of the computer and watch it on ESPN Plus and pay for it that way, right? So, conspiracy theory number one, ESPN started this virus. In Asia, and then seeded it. Anyway, two whole signals generating another whole signal. All right, so that's what convolution was. And we noted that for a causal FIR system, a system that takes input signals x of n and gives you output signals y of n, we have y of n equals h of n convolve with x of n, where h of n is the system's impulse response. What is the impulse response? It's what you get at the output when you use a delta at the input. And at the very end of class last time, we were addressing the following major fact about general LTI systems, and that is that this is true. In other words, output equals impulse response convolved with input. That's true for general LTI systems, not just causal FIR systems. So important fact. This last item, this last assertion, let's glamorize it, is true for general, at least sufficiently well-behaved LTI systems. Why? Let's see. Here's the picture we had on the board at the end of class last time. Suppose we have an arbitrary input signal x. So say x of n is some input signal. And say h of n is the system's impulse response. Let's draw some pictures. And this lineup of pictures, each of these pictures is whole signal in, whole signal out. So on the left column, I'm going to have whole signals. And on the right column, I'm also going to have whole signals. And this is what's you're going through the system. All right, so if I put whole signal delta of n into the system, what comes out? Want to tell me? Yeah, whole signal h of n. What if I put whole signal shifted by 1 delta in? What comes out? Yes. h of n minus 1. Why? Because the system is time invariant. If you shift an input by a certain amount, then the output signal corresponding to that input gets shifted by the same amount. So this is because time invariant.
You dropped -1.
Oh, thank you, Alex. All right, similarly, if I took delta of n minus 2 into the system, that's whole signal goes in. What comes out is whole signal h of n minus 2. Again, because time invariance holds. And this is true for all the shifts of delta. In fact, it's true for the negative shifts. So if I shift delta to delta of n plus 1, that's a delta shifted to the left by 1. Put that into the system, then the whole signal h of n plus 1 comes out. And that's true for all those. OK? All right, and that's all because of TI, time invariance. OK. Now, what happens if I take a linear combo of all these signals, these whole signals? Then, by linearity, the same linear combo of these whole signals comes out. OK, so by linearity, if you take a linear combo of the left signals, then put that into the system, the corresponding output is the same linear combo of the corresponding right signals. And what linear combo am I going to take? Well, what I'm going to do is I'm going to use the numbers, the values of x of n, as coefficients in the linear combo. So let's use the values of x of n, the signal we're going to be considering as an input signal, as coefficients of the linear combo. And what happens? On the left-hand side, we get, going into the system, sum from k equals minus infinity to infinity, x of k, delta of n minus k. And on the right-hand side, we get same linear combo. So this is going to be the same linear combo, k equals minus infinity to infinity, of x of k, h of n minus k. And this, again, this is a whole signal. It's a linear combo of the whole signal delta shifts. This is another whole signal. It's a linear combo of the h shifts. And the coefficients of the linear combo happen to be the values of x. But wait, what is this whole signal? What is this whole signal? This whole signal is the convolution of the signal x of n with a delta. You can think of it that way if you want. Or you can look at it by hand, and you could say, well, what is its value at time n? Well, its value at time n is going to be the value where k equals n is the only one that's non-zero in the sum. You get x of n. Anyway, the left signal turns out to be just x of n all over again, because it's the convolution of a delta with x. And we know from last time that delta of n is an identity element for convolution, the identity element for convolution. So the left signal is just equal to delta of n convolve with x of n, which is x of n all over again, because delta of n is an identity element for convolution. The right-hand signal is just h of n convolve with x of n. And by the way, I'm kind of using the commutativity of the convolution operation. Remember, it doesn't matter who gets the k, who gets the n minus k, result is the same. Bottom line, x of n in, what comes out? Y of n is convolution of h of n with x of n. And that's what we wanted to show, that this last assertion is true for arbitrary LTI systems, subject to well-behavedness. Now where you may, the picky students who are like I was when I was an undergrad, picky, like, wait, where does the sufficiently well-behaved come in? Where did we need that in this whole argument? Well, basically, what we're getting away with here, mathematically, is taking infinite linear combos of input signals and giving rise to infinite linear combos of output signals. And technically speaking, linearity does not provide for that. It only talks about taking a finite linear combo of input signals, giving rise to the finite linear combo of output signals. So that's where you need the well-behavedness. And just for my conscience's sake, I'm going to note that down. We need system well enough behaved so the linearity property applies to infinite linear combos of input signals. And I'm not going to get any deeper into it than that in this context. If you want to learn more about that, you can take EC 3250. And whoever teaches that, that'll be me next fall, will explain what systems don't have this property. OK, so summary. Once again, we have these important pictures and important dueling characterizations of impulse response that we had for causal FIR systems. Now we have them for arbitrary LTI systems. So thus, once again, and I can't emphasize this enough, we have these two alternative, useful views of h of n. View number one, delta of n goes into the system, h of n comes out. It's the response to an impulse. The other one, you put any old signal x of n into the system, then what's happening inside this box is going to be that h of n is getting convolved with x to give you output y of n. So you can think of h of n as coded or wired into the system. It's what you convolve with inputs to get outputs. All right. And it's good to be able to bop back and forth between those views of impulse response. And we'll see an example of that bopping in a moment. OK, so now just for some loose ends from chapter 5. So here's a few sort of loose ends. First off, LTI systems, very important. What about systems that aren't L or aren't TI? What are some examples of those? I mean, we actually, I think the first week of school we talked about this a little bit. But here's first of all, so what kinds of systems aren't LTI? Okay, so how about a simple example? A simple example of a nonlinear system. So not L. Can anybody think of it just a simple example of a system that's not linear? Bryce. You moved your hand. Think of it like an auction, right? You scratch your head, you're making a bid, right? Like Nick discovered that last time when he took his pen and did that you.
What about xn goes to xn squared?
Yeah, great example. X of n example. Great example. How about let's elaborate on that a little bit. So suppose your input signal x of n goes in, and what comes out is y of n is equal to, say, how about 3x of n squared minus cosine of x of n minus 1. How about that?
It's a little more complex here.
Yeah, but you were barking up the right tree, and I just climbed up into the canopy and did that. It's not. You can check it out that it's not linear. Yeah.
Do you have this squared on the inside of the brackets, so it's x bracket n squared, so it's xn. So it's what would happen is if xn was just going 1 0 1 0 or whatever, then it would go at the first n it would be 1, and then at the xn squared it would also be 1, but then at x where n is equal to 2 it would be 0.
Yep.
So then xn where n is equal it would be x bracket 4. Does that make sense? Because the n has the square directly.
Well, the n is not going to have in this case, the not linear thing, the n is not going to have the square.
Yeah.
I'll do a not time invariant where the n has the square.
Oh, that would be not time invariant.
Yeah, but it's not going to be inside the x. It's going to be outside the x.
Okay.
Yeah, this one, you evaluate the input at time n, square it, multiply it by 3, evaluate the input at time n minus 1, cosinify it. Cosinify it? What's the verb for cosine?
I like cosinify it.
Cosinify it. Cosignify, that would be, yeah. And in Italian, it would be cosignifiare or something. Anyway.
Sure.
Sure, right. Okay, have I properly dodged your question, Bryce?
I'll just wait. Maybe.
All right, okay. How about not time invariant? These are, and you're actually going to have I think you're going to have a homework problem where you have to assess a couple of example systems for linearity and time invariant. Typically, what happens for not time invariant systems is you have coefficients, like the BKs, for a FIR system, coefficients that aren't independent of n. And so here's an example of such a thing. Y of n is equal to, how about the sum from k equals 0 to cap m of, say, n plus 1 squared x of n minus k. Something like that. And let's make it even better. How about k n plus 1 squared x of n minus k? Something like that. Now, what makes this not time invariant is this n plus 1 squared. This is the problem. Because if I didn't have that, if I just had k x of n minus k, that would turn out to be time invariant. With bk equal to k for 0, 1 to n. 1 to m, I should say. So without the n plus 1 squared, we'd have y of n equals the sum from k equals 0 to m of bk x of n minus k with bk equals k when k is between 0 and m inclusive, and 0 otherwise. And this whole thing here, this is just a causal FIR system. But if you do the UV thing with the by the way, if you guys weren't here last time, the UV thing is the way I like to test for time invariance. So watch the last video if you want to see that. If you do the UV thing with this, you'll find out that this n+1 thing causes problems. All right, so those are examples of systems that aren't time. That's one loose end I wanted to clear up. Okay? Any questions about that? Another one, cascading systems. What happens when I take two systems and cascade them? Or even three, whatever. What does it mean to cascade systems? It means to build a compound system where the output of one system is the input to the next. So build a compound system where system 1, say system 1's output serves as system 2's input. So picture-wise, we got this sort of thing going on. System 1 here, system 2 here, and our compound system is this big thing that encloses those two. Now, legitimate questions arise. For example, if both systems are linear, is the resulting system linear? If both systems are time invariant, is the resulting system time invariant? Those are legitimate questions, and the answers aren't obvious. It does turn out that if system 1 and system 2 are both LTI, and this is not hard to show, both component systems LTI implies that the overall system is 2. The overall system is LTI as well. Okay. And given that you believe that fact, you might want to ask, okay, suppose that's the case. So everything in the picture is LTI. What is the impulse response of the overall system? And does it depend in some simple way on the impulse responses of the individual component systems? So here's a question. What is h of n? The impulse response of the overall system. Okay. How do you figure out impulse response? Well, you look at the next board. Impulse response, you have two ways of figuring it out, or two ways of thinking of it at least. It's the response of a system to an impulse, and it's also what you convolve with inputs to give you outputs. All right. Suppose h1 of n and h2 of n are the respective impulse responses of the component systems. Respectively. What happens when I put a delta into the overall system? Let's track some signals through the pictures. Because when I put a delta here, the impulse response of the overall system, h of n, is going to come out. So I put a delta into the system. What comes out of system 1? What is this sig? h1 of n. Excellent. Because the impulse response is the response to an impulse. OK? All right. So now I'm putting h1 of n into system 2, and the result is going to be h of n. What comes out when I put h1 of n into system 2? What comes out? Yes, because the impulse response is what you convolve with inputs to give you outputs. Very good. So this is equal to h, and I'll write it this way, h2 of n convolve with h1 of n, just because it matches up better with this over here. So this is because, let's put a couple labels on here. This is, I'll put circled 1 here and circled 2 here. Circled 1 is true because impulse response is response to an impulse. So 1 because impulse response equals response to delta. Circle 2 is true because impulse response is what you convolve with the input to get the output. So we use both of those characterizations of impulse response to conclude that if you cascade two systems, so you cascade two LTI systems with respective impulse responses h1 and h2 of n, means that implies that you get an LTI system with impulse response that's the convolution of those two individual impulse responses. And here I swapped back the order h1 of n convolved with h2 of n just to make you think, oh yeah, right, convolution is commutative in that sense. And byproduct of this is it doesn't matter what order you cascade the systems in. And that's something that's not totally obvious, to me at least. If you came up to me on Ho Plaza and you said, OK, I'm trying to decide whether to hook up the systems in this order or in this order. Which one should I use? It doesn't matter. I wouldn't know that like a priori unless I sort of already knew about convolution being commutative and went through this whole computation. So would that be obvious to you guys, that if you hooked up two things in a different order, you get the same overall result? If it is, your intuition is better than mine about that, at least. So note that it doesn't matter which order you cascade the systems. You're going to get the same overall result. All right. Another loose end. Remember, we're wrapping up some loose ends from this chapter. First one was what's linear, what's not, what's an example of something that's not linear, what's an example of something that's not time invariant. Another one is what happens when you cascade systems. A third one is something I've been sort of promising you off and on this whole time, and that is a sort of a more detailed discussion of what do we mean by causal system, okay, and how do you characterize causality in terms of, say, impulse response, whatever. So another loose end, and this I guess is sort of going to be the final loose end, I think. Let's talk a little more in depth about causality. A word, or at least part of that word, we've been throwing around quite a bit. Every time I mention causal LTI systems, I use the word causal without really talking about it in any depth. All right, so what does causality mean? What does it mean technically? A system is causal, essentially, when it doesn't predict the future, right? When whatever's happening now depends only on what happened up through now, and not on what happens later on. So that's the sort of intuition. A system is causal when the value of the output say at any time, say now, depends, whatever this is going to mean, only on the values of the input at times up to and including now. And not on values yet to come. At values at later times. So that's the intuition. And that seems like a mild assumption on a system, right? Like, you know, certainly anything you could build in the real world, you might say, it has got to be causal, because, you know, you can't build something that predicts the future, even if you believe all those like relativity experiments, you know, like which way did the photon go and blah, 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 blah. Causality seems to be built into the universe. Well, it turns out that's true when the n variable, like the n and the n minus k, but when those things really mean time, this is true. Causality is something that inheres in anything in the real world. But it turns out that in real life, as we'll see, you do use non-causal LTI systems a lot. All right, so let's first of all, let's get at the math of this. Remember, example, we've been talking about a causal FIR system. That's something that has the I/O relationship. Y of n is equal to the sum from k equals 0 to m of bk, x of n minus k for some constants bk. And you can also write this as the sum from k equals 0 to m of h of k, x of n minus k for this system, because that's what the impulse response of a causal FIR system is. It's just the bk's, essentially. All right. Now, this I/O relationship exhibits the value of y of n explicitly as a linear combo of present and past values of the input, right? So, i.e., for any time n, and you can think of the n as being the now in the intuitive definition. For any time n, the value of y of n is a linear combo of the current and past values, a certain subset thereof. So it's a linear combo of current and past input values it doesn't involve values of the input x for times bigger than n. What would be an example of a non-causal FIR system? So here's a non-causal FIR system. The IO relationship is, how about y of n is equal to 1/7 times the sum from k equals -3 to 3 x of n minus k. All right, so I'm going to throw that up on the board and take the 3-minute break, and then we'll talk about that and why you might encounter something like this in real life. And try not to think about the email that Jack told me about early in the class. Nothing like teaching a class to take your mind off an unpleasant event. I wonder if they're going to forbid prelims and where for classes of more than 50 students, you have to take them in separate places.
All the, like there can be no fan, but we can still go take a prelim with 600 people. Like, that's
Yeah, that's really smart, eh? No, yeah. Oh no, people are coming from miles around to the hockey game. They're coming from Elmira and Watkins Glen, those hotbeds of infection. You know, we don't want them bringing this virus to our old people. Yes.
What they should do is just not let anyone who's not a Cornell student into the games. The entire stadium is Cornell.
Yeah, well, they could do that. They could do that. I mean, another conspiracy theory is that the ECAC does not want to be unfair to any of the home teams, and so they're not letting any home team have fans this weekend. Okay? Now, that's unfair because we have the best fans, and so, yeah.
It's all Harvard.
That's what the males do.
They don't want to lose.
Yeah. So anyway, I don't know. This is crazy. This is really annoying. Really annoying. But because teaching you guys in class is the funnest part of my job, I'm going to try to ignore the hockey stuff and think about systems. All right. So here's a non-causal FIR system, right? Now, why is it not causal? Because for any n value, this y of n depends on the x values in a window of length 7 centered on time n. So it depends on the previous 3, the value now, and the next 3. Okay, so i.e., for any n, y of n is equal to the average of the 7 input values in a window centered on time n. So just like the causal FIR systems, this is a sliding window. This system operates in a sliding window fashion. The only difference is that the window at any time n, that computing y of n doesn't just compute values to the left and do something with them. It uses values to the left and to the right. And you may say, well, you know, how could you ever build something like that? Well, you can't if n really means time. Okay? So if the quote-unquote n variable really means quote-unquote time, you can't build this. But clearly, you know, the universe did not end when I wrote it on the board, right? Like, the solar system did not disappear into a black hole. Well, Cornell hockey didn't let their fans come. But nothing huge, no big cataclysmic occurrence took place when we wrote that on the board. So clearly, it's not sort of in a universal sense illegal. So where might this arise? Where might a system like this arise and be useful to you? So really, Bryce, what's an example?
Like a preset data set.
Yeah, exactly. Like, this comes up all the time in data science and machine learning. data post-processing is the kind of universal term I apply to it, where you want to say smooth out a data set, right? This is a way to smooth out the data set. It takes local variations and kind of averages them out. So these kinds of systems arise, what makes it work, what makes it not illegal mathematically is that n doesn't mean time here. It just means like position in the data set or index of a piece of data. But these come up all the time when you're doing data post-processing. And what makes it legal is that the n variable, quote unquote n variable, that's really ugly instantiation of variable. So let's make it nicer. N variable indexes position in data set rather than time. And there's all kinds of 2D versions of this for denoising images, whatever. You know, they come up all the time. But anyway, those are non-causal systems. Now, in general, when you have an LTI system, these are just FIR examples. When you have a general, yes, Jack.
So you say this works for data sets, but what if the position in the data set corresponds to a given time? Like
Well, maybe it did correspond to a given time, like when you built up the data set, right? But now you have it. Those times are all in the distance past, and now you're going to manipulate it.
So it's more about the time in like a time sense, not in a data sense.
Exactly.
Like,
I mean,
you could then smooth the data set and then plot it against time. But that's still legal?
yeah, but the thing, when I say if the n variable really means time, what I mean is, can you build a box, right, where if I take an input signal and I plug it into the box, this signal comes out of the box?
Okay.
You know, while I'm watching.
That'd be quite a box.
That would be quite a box, yes, exactly.
Okay.
And the answer is no. But you can build a box so that if you have some pre-thing, you know, a bunch of x's kicking around, you know.
In that sense, it is all past time, even if it's forward time from the reference frame.
Yeah, in that sense, yeah, right. OK. All right, so what, like, clearly, because we know that the impulse response of a system, of an LTI system, tells us everything about the system. OK, so now, the impulse response, h of n, of an LTI system characterizes the system completely. This is my sister and her husband expressing their regrets about what Cornell did. OK, Tom, who played goalie for Union, my brother-in-law, says, bummer. OK. All right. Back in the 80s, he was played goalie for Union. OK. Characterize a system completely. I hate getting text in the middle of words, but it happens all the time. Since the impulse response of a system characterizes the system completely, we ought to be able to talk about causality in terms of the impulse response. So there must be a way to characterize causality in terms of h of n. And here's that way. Fact. A system with impulse response h of n is causal turns out to be true if and only if h of n is 0 when n is less than 0. Simple property of h of n, equivalent to causality. All right, so let's look at this real quick and see why it's true. First, why is that true when the system is causal? So let's look first at causal implies that h of n is equal to 0 for n less than 0. And here I want to think about h of n as the response to an impulse. OK? All right, so h of n, remember, it's the result of one particular I/O experiment on the system. You walk into the room, you find the system on the table, you hit it. You hit the red button, you kick it if you're a little kid, you throw it, whatever. So that's the impulse response. Now, if the system is causal, there's nothing happening at the input until time 0, right? Nothing happening at the input until time 0. So there can't possibly be anything happening at the output until time 0, right? Because otherwise, the system would kind of know that something was coming, right? Does everybody buy that? If the system is causal, causal implies nothing happening at the input for times n less than 0, which in turn implies nothing at the output for time n less than 0. And this is when delta of n is the input signal, which implies that nothing is happening at the output for time n less than 0 when delta of n is the input signal. And that is the same as saying that h of n is 0 for n less than 0. So that's a simple, intuitive argument for why an LTI system that's causal has an impulse response that doesn't turn on until time 0. Now let's look at the converse. So as for the converse, that is to say, h of n 0 for n less than 0 implies causal. Let's look at the other way of thinking about the impulse response, namely what you convolve with inputs to give you outputs. First, we used impulse response as a response to an impulse. Now we use the fact that for any input signal x of n, y of n is equal to the convolution of h of n with x of n. So for any time n, we have that the value of y at time n is this. The sum from k equals minus infinity to infinity of h of k x of n minus k. I'm going to reject this call no matter who it's from. Phantom number that looks like a cell phone, local cell phone number. I hate that. Do you guys ever get the spam calls from 212 and 202 numbers where it's someone speaking Mandarin? Yeah, and she's telling you, it turns out I asked a friend of mine who speaks Mandarin to tell me what they were saying. And roughly speaking, they're saying that you must hurry down to the consulate or your passport will expire and you will turn into a pumpkin or something along those lines. And so you get those, right? Right, OK. And I'm safe ignoring those, I think? Yeah, OK. All right, so we have this. Okay, now if you assume in addition that h of n is 0 for n less than 0, this becomes the sum from k equals 0 to infinity of h of k, x of n minus k. And this is when h has this property that it's 0 for negative values of time. And what that does is it exhibits explicitly the value of the output at time n as a linear combo of present and past values of the input signal, not future values. So this is a linear combo of values of the input signal at time n or before. And since this is true for arbitrary inputs, the system is causal. So this is true for arbitrary inputs. That means the system is causal. So causality in terms of the impulse response is just impulse response is 0 for times less than 0, period. Okay. Now there's one other thing in chapter 5 that they do that I think is kind of trivial, and I don't like to waste lecture time on it, but I'll just point out that and some of this will be in the handout that does the pesky boundary case at the end of the semester that you will get before the final, despite Alex's original assertion that he didn't get it until after the final, which was not true. One more thing from chapter 4, or chapter 5, right, that we're talking about now, that I don't want to spend a lot of lecture time on is block diagrams. It's so easy. Let me just give you an idea. You end up with little pictures that sort of show you how a system operates. The pictures are composed of delay blocks and coefficient multipliers. So for example, let me just do an example. Suppose I had this system. Suppose I had y of n is equal to, say, 3x of n plus or minus 5x of n minus 1 plus 7x of n minus 2. That's a causal FIR system, right? The IO relationship for a causal FIR system. How might you represent that in a picture? Well, you're going to have x of n coming in and y of n coming out somehow. And there's loads of ways of doing this. And some people like to do their block diagrams this way. Some people like to do them this way. Very few people like to do them this way or this way. But you get the picture. No pun intended. So say x of n goes in. And remember Rick Johnson, my colleague from Macon, Georgia, sometimes talks about these causal FIR systems as tap delay lines, right? So you take x of n and you put it into a delay line, OK? So you delay it by 1 unit. So unit delay. What does that mean? What comes out there, here's x of n minus 1. That's what's on this branch. And you delay it by another unit. So here's another unit delay. And what comes out of there is x of n minus 2. And how do you get y of n? Well, you tap the delay line, OK? You take 3 of these and add it to minus 5 of these and add that to 7 of these and voila, y of n comes out. OK? That's an example of a block diagram. End of story. OK? You read the book, you want to learn more. And it turns out that later on in the class when we talk about IIR systems, these turn out to be more significant. Okay, so that wraps up pretty much the chapter 5 stuff on FIR systems and general LTI systems. Any sort of general questions on that before we move on to the frequency response material, which is a crucial, important part of the class. Everything's crucial and important. So. It just occurred to me that you know, there's 4,100 of us and only about, I don't know how many people in CUPD, you know. Exactly. We could stow away in the building overnight. I know people, I know Phil Graham, the guy who sweeps the ice, you know. I can hide in the skate sharpening room. Yeah, and I can unlock it for you. That's, hey, that would be cool to have a fan revolt of that kind, you know. Anyway. All right, I've given you more time to think of a question. Have you thought of one? Yes?
You're not going to like this question, but what's that last line on that farthest board that you wrote?
I have no dislike for this question. The very last line or the last two?
You can do the last.
Okay. This equals a linear combo of values of input signal at times n or before. Got it? Why wouldn't I like it?
Because it's not like a content question.
Sure it is.
I can't see it.
There's content in this. I'm never going to put a content-free sentence on the board, so you know, it's fine.
It's impossible to read like that side of the board when you're sitting on that side of the room, and vice versa.
Well, I try, like, tell me if I need to move the international date line to the left or...
It's nothing that can solve, because it's like that entire right whiteboard is just...
Yeah, here's the view in Carpenter Hall is that 203 and 219 Phillips have problematic aspect ratios. Okay, I've literally seen that phrase used, okay? Problematic aspect ratios, okay? And so what they're going to do, they're going to take one of these rooms, I think 203, and turn it into a collab spacey kind of classroom where it's easy to flip the classroom and that, you know, do these modern things. And they're going to take out the blackboards and put in whiteboards and have them on all the walls. And I hate whiteboards, and so does most of my colleagues hate whiteboards too. The pens never work, it's hard to write on them, you know. Let me count the ways. So, you know, it's funny how the teaching theorists come up with these cool ideas, and sometimes we're surprised that they actually work. But I think you guys are going to be the test kitchen people, you know, and come back and say, you know, it doesn't really work, or it does work, whatever. But that will eliminate this problem of invisible left board, right board.
By just getting rid of the room.
Yeah, just getting rid of the room and turning it into a, you know, I've seen actual pictures of what it's going to look like, and I don't fully understand the table setup, you know. But anyway. Any other questions? Yeah?
So about that third board there.
Yeah.
You were talking about, and I think this is a cool argument. Like if h of n is equal to 0 for n less than 0, then it must be causal.
Yep.
But does this allow for any sort of like weird piecewise functions or some sort of function that's causal for less than 0, but then non-causal greater than 0?
No, causality is a property of the system, overall system. Like for any, see, h of n is a signal, right? That signal has properties. One property it could have is that it is 0 for n less than 0, that signal, that particular signal. If that particular signal is 0 for n less than 0, then for every input signal, the value of the output at any time n depends only on the current and past values of the input at time n. Okay, so the assertion is this property of h of n equals 0 when n is less than 0. That's property of one signal. That's enough to guarantee that for any input signal, if I put it into the system, the value of the output at any time depends only on the current and past values of the input. And that's true for all times.
So if you had a signal that was, like you said, 0 for n less than 0, but then
The output will be 0 for n less than 0.
but then non-causal for n greater than 0?
No, no. For n bigger than 0, the value of the output, say at time 7, will depend on the values of that signal up through and including time 7, and not the ones after time 7. For time 13, it will depend on the values of the input up through and including time 13, but not after.
Yeah, but wouldn't that satisfy this this sort of requirement that you had this sort of weird signal that was non-causal later, but still satisfied this requirement?
Signals can't be causal or non-causal. Systems can. Does that make sense? Causality is a property of systems. Causality is about not predicting the future. Signals don't do anything but exist.
Oh, sorry. So if the system is has this property where it's 0 up until n, 0 up until 0.
Okay, wait a second. Systems aren't 0 up until signals are. Okay, systems are causal. Signals have 0 properties, right? So, let me. Are you going to fix his?
Maybe.
Okay, Nick's going to give it a try. Yeah.
What if it's like, so we had the averager from like -3 to 3.
Yeah.
What if we said for the first, like, if n is between 0 and 3, like it has a coefficient of 0 in front of it. So we make some garbage rule that makes it,
Yes.
make it fit that.
That'll make it a causal system.
Even though that afterwards it'll still be between.
No, if it's time invariant, you can't have that change. You can't have that change.
Okay.
The window has to stay the same and slide along.
Yeah, the time invariance protects against that.
Okay.
Yeah.
So we're good. Yeah.
Okay, we're good. So, okay. All right, well, remember, Thursday, that post-break part of the class, come prepared with questions.